record. Okay, I'm now recording. No problem. Yep. Okay, so I got it. Okay, so we're going to go over number 3. So evaluate that determinant. Okay, so now I'm going to go to Word. So you should see Word now on the screen. Okay, so we're going to go over this problem. I think it was number 3 on the sheet. Number 3. Okay, good. Okay, good. Okay, so this is equal to. So now, okay, so you could do the cofactor expansion along the first row. And so you have 3 times one determinant minus -1 times another determinant plus -2 times another determinant. Okay, so for the first determinant, it's of the determinant 5, -3, 3, 7. And so for the next determinant, it's 2, -3, 2, 7. And then the next one, it's 2, 5, 2, 3. Okay, so now you just evaluate that. So it's 3 times that determinant, which is 35 minus -9. 35 plus 9 is 44. Then minus -1 is +1. It's plus the next derivative, which is 14 minus -6. 14 plus 6 is 20. And it's -2 times that derivative, which is 6 minus 10, which is -4. So this is equal to 130. 3 times 44 is 132, plus 20 plus 8. And so if you add that, you get 160. Okay? So the determinant of that matrix is 160. So that's the answer to number 3. Okay, so we start off with an easy one. Okay, so let's look at another one. Let's find the characteristic equation, the eigenvalues, and bases for the eigenspaces of that matrix. Okay, so let's find first the characteristic equation for that matrix. So to find the characteristic equation, we want to find the solutions of lambda I minus a. The determinant of lambda I minus a is equal to 0. Okay, so that's the same thing as the determinant of A. I'll remind you, A is this matrix. A is the matrix 1, -3, 3, 3, -5, 3, 6, -6, 4. That's A. So we want the determinant of lambda I minus A. So we get lambda minus 1. We get 3, -3, -3, lambda plus 5, -3, -6, lambda plus 6. Oh, no. 6. And then lambda minus 4. Basically, you're taking the negative of all the entries in A, and then you're adding lambda on the main diagonal. So the determinant of that matrix is equal to 0. So we can take the cofactor expansion along the first row. Okay, so I'm going to take the cofactor expansion along the first row. So you get lambda minus 1. So it's just like normal determinant times the determinant of lambda plus 5, -3, 6, lambda minus 4, minus 3 times the determinant of -3, -3, -6, lambda minus 4, plus the next entry, which is -3, times the determinant of the corresponding submatrix, which is -3, lambda plus 5, -6, 6. Okay, And so that's the determinant, and it's equal to 0. So you get lambda minus 1 times the determinant of that submatrix, which is lambda plus 5 times lambda minus 4 minus negative 18 or plus 18. So you get lambda squared plus lambda minus 20, and then minus negative 18 is plus 18. So that's the determinant of that matrix, and then it's minus 3 times that determinant, which is negative 3 lambda, and then plus 12, but then it's minus 18. Plus 12 minus 18 is minus 6. And then it's minus 3 times the determinant of the next submatrix, which is now negative 18 minus negative 6 times that, or that's plus 6 times that. So it's plus 6 lambda plus 30. And that's equal to 0. So now if you multiply lambda minus 1 times lambda squared plus lambda minus 2, this is minus 2, right? So negative 20 plus 18 is minus 2. So now lambda minus 1 times that, you get lambda cubed. You get plus lambda squared. I'm multiplying everything by lambda, minus 2 lambda. Now I'm multiplying everything by minus 1. So you have minus lambda squared minus lambda plus 2. And so that's the first thing. Now it's minus 3 times that. So it's plus 9 lambda plus 18. Then minus 3 times this. Now negative 18 and 30 adds up to positive 12. That's a plus 12 there. So it's negative 3 times 6 lambda plus 12. So that's minus 18 lambda. And then minus 36. That equals 0. You add common terms. So you have a lambda cubed. Okay, you have a lambda cubed here. And then the lambda squares is lambda squared plus negative lambda squared. That's it. So they cancel. There's no lambda squares. Then for lambda, there's negative 2 lambda, negative lambda, 9 lambda, and negative 18 lambda. So when you add those, you get negative 3 lambda, 6 lambda, you get negative 12 lambda. You get minus 12 lambda. We already accounted for the lambda cubed. And then the constants, we have a 2, 18, that's 20, minus 36 is minus 16. There's a minus 16 here. So we have lambda cubed minus 12 lambda minus 16 is equal to 0. Okay, so now we want to try some numbers here. So because we have integer coefficients and the leading coefficient is a 1, this is 1 lambda cubed, then the possible values of lambda you can plug in are divisors of 16, negative 16, which is plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, or plus or minus 16. So I want to make your life simple, so you want to choose a small one. If you put in 1, you'll get 1 minus 12 minus 16, which doesn't work. If you put minus 1, it won't work either. So my first guess is why not try 2? Okay, so 2 to me seems like a good guess. If you plug in 2, you get 2 cubed minus 12 times 2 minus 16. So 2 cubed is 8. 8 minus 12 times 2 is 8 minus 24, which is minus 16. And then it's minus 16, so that's work. So why not negative 2? So let's maybe negative 2. So negative 2 cubed is minus 8. And then minus 8 minus 12 times negative 2. Negative 12 times negative 2 is positive 24. So you have negative 8 plus 24, which is positive 16, minus 16 is there. So lambda minus 2 is the solution. Okay, so if lambda equals negative 2, that makes that equation hold. So if lambda equals minus 2 is the solution, that means lambda minus negative 2 is a factor of that polynomial, or lambda plus 2 is a factor of lambda cubed minus 12 lambda minus 16. Now, if you divide that polynomial by lambda plus 2, and you do the division, you'll get you'll get, if you divide that polynomial by lambda plus 2, you'll get lambda squared minus 2 lambda minus 8. Okay, and it's still equals 0. So now you just have to factor this, but this factors to lambda minus 4 times lambda plus 2. So you get, this is the lambda plus 2. And then the other polynomial factors to lambda minus 4 times lambda plus 2. Right? So you have a minus 4 lambda plus 2 lambda, which is minus 2 lambda. Negative 4 times positive 2 is negative 8. And lambda times lambda is lambda squared. So that's the factorization. So this becomes lambda plus 2 squared times lambda minus 4 is equal to 0. Okay, the two possible solutions are lambda equals negative 2 and lambda equals 4. These are the two eigenvalues you get for this matrix. Okay, so we found all the eigenvalues in this way. Now, the other thing it says, find the characteristic equation, find the eigenvalues, and bases for the eigenspaces of the matrix. Bases for the eigenspaces of the matrix. Oops. Okay, so the characteristic equation, you could say, is this. So if you got to this point, you have the characteristic equation, okay, with the cube there. So that would be the characteristic equation. These are the eigenvalues. You want to find now the bases of the eigenspaces corresponding to each eigenvalue. Let me just check that one more time. Bases. We want to find bases for each eigenspace. Okay, so let's work on that. So we have lambda equals negative 2 and lambda equals 4. Let's start with lambda equals 4, since 4 is an easy number. So the eigenspace corresponding to lambda equals 4 is all the solution vectors x to 4i minus a in parentheses times x is equal to 0. So all the vectors x that satisfy this equation is the eigenspace corresponding to lambda equals 4. And so to solve that, just think we have the linear system of 4i minus a. Now 4i minus a is just this thing when lambda is 4. So what you have to do is plug that lambda equals 4 into that to get 4i minus a. And so if you plug in 4, you get a 3 here, you get a 9 at the other main diagonal entry, and you get a 0 there. So you get 4, 9, and 0 on the main diagonal. You have a 4, 9, and 0. And all the other entries, there is no lambda there. These are the zeros because we're expressing the linear system represented by that matrix system, by that matrix equation representing it by an augmented matrix. So the 0 is on the right side because there's a 0 on the right side of that equal sign. The other entries don't have lambda in it, so they're the same. So you have 3, negative 3, negative 3, negative 3, negative 6, 6. Okay, so I'll write that down. And then the other one is negative 6, 6. So this is the augmented matrix that represents the linear system represented by this matrix equation. Okay, so the solutions to the linear system corresponding to this augmented matrix are all the solutions x to that matrix equation. So you just want to get this to reduced echelon form and find the solutions for it. So getting this to reduced echelon form, let's say I multiply the first row by 1/4. So 1 3/4 minus 3/4. And that's 0. And then in the next row, let's say I take 3 times that row and add to the second row to get a 0 here. So 3 times this new top row to the old second row. So you get 0, 9/4 plus 9, which is 11 1/4. I'm going to write as a mixed fraction. It's 11 1/4 because 9/4 is 2 1/4. 2 1/4 plus 9 is 11 1/4. And so that's 3 times negative 3/4, which is negative 9/4. That's negative 2 1/4 plus negative 3 is negative 5 1/4. And that's a 0. Now to get the last row, I'm going to take 6 times the top row and add it, the new top row, and add it to the old bottom row. So I get a 0 here. 6 times 3/4 is 18/4, which is 4 1/2. So you get 4 1/2 plus 6, which is 10 1/2. And then, so now it's 6 times negative 3/4, so it's negative 18/4. That's negative 4 1/2. Negative 4 1/2 plus 0 is negative 4 1/2. And you have a 0 here. Okay, so the goal is get this to reduce our echelon form. Okay, so the top row is 1 3/4, negative 3/4, and 0. 0. Now 11/4 is the same as 45 over 4. So I'm going to multiply the second row by 4 over 45 to get a 1 here. So if you multiply this row by 4 over 45, this entry is negative 21 over 4. So if you multiply by 4 over 45, the 4's cancel. And so you get a 45 in the denominator. The 4's cancel, and you get a negative 21 in the numerator. There's a negative 21 over 45. Okay, and then this is a 0. Okay, so now to get the bottom row, we're just going to take negative, so 10 1/2 is 21 over 2. So I'm going to take negative 21 over 2 times the second row and add it to the old third row. Okay, so this becomes a 0. And then I'm going to take negative 21 over 2 times that and add it to this. Okay, but I'm gonna point something out here. I'm gonna get a number here, right? And this is gonna be a 0. And then I could just multiply this row by the reciprocal of this number, and then it would become a 1. So I don't want to calculate this because I know that the next step would be just making this a 1. Okay, so now that's a 1. And then you can take, you can, now that this is now corresponds to the 0, I can add suitable multiples of this, the things above it, to make these 0. So this can be a 0, and this can become a 0. And I can take this thing and add it to here and make this a 0. And so now I get the identity matrix here. So the only solution to x is equal to 0, 0, 0. That all three components have to be 0. That's the only solution to that. Okay? So the eigenspace is just the 0 set. Okay? And so a basis for the 0 set is just the empty set. So a basis for the eigenspace corresponding to lambda equals 4 is the empty set. Okay, so now the other value is lambda equals -2. So for lambda equals -2, we also have a corresponding eigenspace. It's just plugging in -2 into here and solving the system -2i minus a times x is equal to 0. So we want to find all the solutions x to that matrix equation. Okay, so to do that, we're just going to now plug in -2 into our original matrix. So we get -3, 3, -6. The other entries are unaffected, so they'll be the same. So it's 3, -3, -3, -6, 6. Oops. 3, -3, -3, -3, -6, 6. Okay, and then this is the zeros here. Okay, so I'm going to multiply the first row by -1/3. So -1/3. Now we're going to take 3 times the top row and add it to the next row, the new top row to the old second row. So you get a 0, 0, 0, 0. I'm going to take 6 times the top row and add to the old third row. And you get 0, 0, 12. Zero. Okay, I'm going to move the third row to the second row and then multiply it by 1/12. So this becomes a 0, 0, 1, 0. When I switch the second and third rows, now I have all zeros here. And the top row is unaffected, so it's a -1, -1, 1, 0. And if I take -1 times the second row and add it to the top row, I get a 0 here instead. So now this is now the solution space, we see we have a leading one here and a leading one here. And so the only free variable is x2. It's the only one that does not correspond to a leading one. So x2 is equal to t, which means that x1 is equal to x2, which is t, and x3 is equal to 0. So the solutions to this eigenspace of the form x1, x2, x3, where x1 is going to equal to t, x2 is equal to t, and x3 is equal to 0. This is equal to any real number t times 1, 0, 0. And so a basis for this eigenspace is just the vector 1, 1, 0. That's a basis for this eigenspace. Okay? So now we have a basis for each eigenspace. And so we are now done with that problem also. Okay, so I will put this up on, remind me to save the whiteboard, and then all this can be on YouTube also. Okay, so class time is ended now. And so I need to give you the time to send me your exam solutions to exam 2. So, so if you want more help for the final, if you want to make sure I receive your exams, then be at the meeting that starts at 11:10. Okay, so I will send the Zoom invite to your Blackboard emails at 11:10, and so I'll see you then, right? And also don't forget that the final for this class is on December 21st from 8:30 p.m. to 10:30 p.m. And I will send you the Zoom link for the final the day before the exam, okay, to your email associated with Blackboard. Okay? Okay, so send me your exam answers. They're due by 10:45 p.m. tonight. So your exam answers are due by email by 10:45 p.m. And the Zoom meeting will start at 11:10 p.m. The Zoom meeting is optional. Okay, have a good night, and I'll see you soon. Okay, save the whiteboard.
Thank you, Professor.
You're welcome. All right, good night.
Good night, Professor.
Good night. Thank you for taking my class, by the way. And
thank you for bringing our professor.
all right, so class things will be open again next semester, so I'll see you.
Oh wait, Professor, I have a question.
Okay.
Do you teach next semester, or you don't teach at spring, right?
No, I do teach in the spring. Yeah.
Oh, I never saw you for like 231 or 241.
Oh, actually, I've taught it a lot of times. I've taught 241 a lot of times. I've taught 231, but I wasn't teaching 231 for a few semesters.
Oh,
like 1 or 2
okay.
semesters. So that's probably why you didn't see me for 231 until now. Yeah.
Okay, but you're teaching for 241 next semester?
Yeah, I am. Yeah.
Okay.
So if you want to take me again,
well, I have taken your class before. I'm just asking. For
okay, yeah, I've seen. Yeah, I remember.
You do? Really?
Yeah, I remember names sometimes. Sometimes I remember faces. I'm not the best at remembering names. I'm not the best at that. I had a friend I knew for a year, and I forgot his name. But I'm not very good at names. But I do remember your name.
Okay.
But yeah. So all right. So maybe I'll see you all soon. I have to go again. So I'll see you all later. Good night.
Good night, Professor.
Good night, Professor.
Good night, everybody. Good night.